Lean in, okay. All right, thank you for the introduction. Today I am presenting results from an ongoing investigation of residues left on papers treated with rigid polysaccharide gels, specifically agarose and gelling gum. This research began in 2014 when I was a graduate intern at the National Gallery of Art in Washington, D.C., and where I worked collaboratively with Barbara Berry, head of NGA's Department of Scientific Research, and Teresa Duncan and Richard Weiss of Georgetown University's Department of Chemistry. Our motivation for undertaking this research is the notably increased interest among paper conservators over the past decade to incorporate gels, both rigid and viscous, into their treatment toolkits. This brief and probably a little bit illegible bibliography illustrates the uptick in the use of gels by paper conservators. And by the end of the day tomorrow, I know I'm going to have to update this slide with many more wonderful publications. So as we've already seen in some of the talks at this conference, the increased interest in gels among paper conservators is an understandable phenomenon. When tailored to treat a paper object with a specific conservation issue, rigid gels can offer a number of advantages. Here, for example, a rigid agarose gel was very effective in locally reducing a tide line in a book page. In this case, the gel afforded restricted lateral flow of solvent and precise application needed to treat the stain in situ within a bound volume. In a second example, a large sheet of 1% weight volume gelling gum was used to wash an embrittled newsprint. The paper was extremely fragile and prone to breakage with even minimal handling. Given its condition, the paper would not have been able to withstand a traditional immersion bath, but it certainly benefited from removal of acidic degradation products, regaining mechanical strength and improving its visual appearance. In this instance, the gel in bath provided an ideal alternative, providing even and efficient cleaning while virtually eliminating physical manipulation. After bathing, while the sheet was still wet and positioned on the gelin, a dilution of methyl cellulose was applied as a surface sizing to further strengthen the sheet. Ultimately, I was really pleased with the final result. The newsprint not only improved aesthetically, but it regained sufficient strength and flexibility to be inlaid for double-sided display, as was requested by its owner. So I'm a really big gel fan. Any of you who know me can vouch for that. And I routinely use rigid gels in treatment, having spent quite a bit of time exploring ways to tailor them to the unique challenges of paper and photographic materials. But I'm also a critical consumer, as I think most of us are, and I felt that more work should be done to understand how rigid gel treatment affects paper objects in the long term. And fortunately, I found a fantastic group of scientists in Barbara, Teresa, and Dick, who were all interested in collaborating on a study to answer this primary research question: do rigid polysaccharide gels leave residue on paper? Given their physical properties, it's tempting to assume that agarose and gelling gum do not leave behind residue. But looking at the chemical structure of the gel polymers and that of cellulose, all of these materials being polysaccharides with many similarities and shared functional groups, we were not convinced that gel residue on paper is actually zero. And if the answer to the question is yes, rigid polysaccharide gels do leave behind residue, we also wanted to know, what are the factors that impact residue? Is it possible to prevent residue deposition? And is residue even problematic, a point that Paolo Cremonese touched on yesterday during Q&A? With these research questions defined, we designed a series of experiments to address them. Our experiments compared two rigid gels, agarose and high acyl gelling gum, with viscous gel-like methylcellulose. Methylcellulose was included, as it has long been favored by conservators, as an adhesive, consolidant, and poulticing material. Further, conservators have acknowledged and accepted that this viscous gel cannot be fully cleared from porous substrates like paper. In all of our experiments, agarose and gelling gum were prepared at 5% weight volume and methylcellulose at 4% weight volume, all relatively high concentrations chosen because they would be suitable for many localized paper conservation treatments. In our experiments, residue was detected visually by tagging the polysaccharide polymers with a fluorescent dye, specifically fluorescein. Fluorescein was substituted at a very small percentage, about 0.001%, of hydroxyl groups in each of the polymers. This slide shows the chemical reaction schematic for covalently bonding fluorescein to gellan gum, but the process was the same for all three hydroxyl-containing polymers. Fluorescein was selected as the tag because it is easily detected, even at such a low concentration. In these spectra, you see the peak excitation wavelength for the fluorescent tag is 498 nanometers, and the peak emission wavelength is 512. After synthesis, the tag gels were extensively rinsed to remove excess fluorochrome and thoroughly dried. Gels were prepared using standard methods. Agarose and gellan gum were dissolved into hot water with calcium acetate added for the gellan and stirred constantly to prevent clump formation. Once fully dissolved, the gel solutions were cast into small trays and allowed to cool. Methylcellulose was added to cold water and stirred periodically over the course of a few days until fully dissolved. So in all of our experiments, residue was detected by placing a prepared tag gel on a paper sample, removing the gel after a defined period of time, exposing the paper to a specific wavelength of light, in our case 450 to 90 nanometers of blue light. And if residue was present, the fluorescein that was bonded to the polymer residue is excited and emitted a green fluorescence at 512. Because fluorescein bonded more readily to some of the gels than others, UV-vis spectroscopy was used to analyze dilute solutions of the tag gels and calculate the percent attachment of fluorescein. Based on these calculations, untagged polymer was added to the gel solutions as needed to ensure equivalent amounts of attachment were present in each of the gels. In other words, to make sure there wasn't a significantly higher amount of fluorescein bonded to one gel than another, leading to a false interpretation that one may be leaving more residue than it actually does. And to confirm, fluorescence spectra, the spectra you see on this slide, were measured from prepared gellan gum, agarose, and methylcellulose. And as you can see, despite slight differences, the fluorescence spectra for the three gels are comparable and indicate comparable degrees of fluorescein attachment. Finally, dilute gellan gum solutions, buffered across a range of pHs from 5 to 9, were prepared to confirm that slight differences in pH of the gels would not significantly impact fluorescence and ensure emission was not different or stronger at one pH over another, which could again lead to a false interpretation of relative residue amounts. Across our study, 3 different papers were used. The papers were selected because they have different physical qualities and are representative of the range a paper conservator might encounter in a fine art or archival collection. The papers we selected were Whatman filter paper with 100% cotton linter fiber content and an open, unsized surface, Barcham Green Hale, a lightly textured handmade rag paper with cotton and linen fiber content and a gelatin surface size, and Mohawk Superfine, a machine-made, chemically purified wood pulp paper with many inorganic fillers and a slick calendared surface. And the image on this slide shows a simple contact angle test that you've already seen a few times in this conference, in which a simple application of a water droplet demonstrates the variable wettability of the 3 papers. Standard polarized light microscopy was used to confirm the fiber content of the papers, and imaging with a scanning electron microscope helped further characterize how open or closed their surfaces are. SEM also helped us better understand the presence of fillers and why a paper may or may not be more or less susceptible to receiving gel residue. Across our study, gels were applied at 3 different time intervals, 10, 20, and 40 minutes, to reflect durations a conservator might use during treatment dependent upon application. In addition to the variables of paper and time, several treatment modifications were tested as well, with the aim of reducing or minimizing potential residue. The variables tested in this study included the use of a Japanese tissue barrier layer, damp swab clearance immediately following gel removal, and in the case of gellan gum, varying the amount of calcium acetate added to the deionized water used to prepare the gel. Following each of the experiments, residue was visually evaluated and documented by 3 methods: microphotography using a fluorescence microscope, fitted with a mercury arc lamp, an I3 filter cube, visible light macrophotography, and ultraviolet-induced fluorescence macrophotography using UV lamps and a Canon DSLR camera. In total, our study included 3 distinct experiments, which we refer to in the conference publication as the residue study, the clearance study, and the calcium acetate study. The variables tested in each of these experiments are summarized in the table on the slide. I will begin by describing the residue study and the observations that we gleaned from it. This study compared agarose, gelling gum, and methylcellulose applied to all 3 papers at all 3 time intervals, with and without the use of a Japanese tissue barrier layer. On this slide, you see a grid of macro UV photographs from the residue study. Paper samples are listed down the rows, and gels and the treatment variables across the columns. And throughout our presentation in the written paper, images are presented in this format. Also throughout, images represent results from the 40-minute test interval, kind of to save space. And we should just note that the results observed at the 10 and 20-minute time intervals are consistent with what we observed at 40, so no significant outliers. And before moving forward, I should mention one thing on this slide, that unfortunately our Whatman filter paper contained a fluorescent water-soluble material that can kind of confuse interpretation. So you see a white tied line that's pretty fluorescent, but it is different in color and appearance than the gel residues that kind of appear green because of the fluorescein. So just to point that out, we didn't expect an optical brightener to be in our laboratory grade filter paper, but it was. Okay, so the residue study. While we hesitate to make any real definitive conclusions without further research and experiments, we did observe some general trends as we reviewed the images. Comparing the 3 gels at the macro level, we see gelling gum appears to leave behind more residue than agarose and methylcellulose. And across the 3 papers tested, Whatman filter paper appears most susceptible to gel residue, more so than the handmade rag or the machine-made paper. And if you think back to the SEM images and how open that paper surface is, it really makes a lot of sense intuitively. Likewise, the machine-made wood pulp paper, with its calendared, slick, compact surface, appears the least susceptible to the papers tested. And across all of the papers and gels, the Japanese tissue barrier layer appears quite effective at preventing, or at least minimizing, gel residue deposition. Now zooming in, we have the photomicrographs captured with the fluorescence microscope. All of these images are captured with a 20-power objective. At the micro level, gelling gum again appears to deposit more residue than the other 2 gels. But at this level, the handmade gelatin-sized rag paper appears more resistant to gel residue, and not the machine-made paper. And actually, contradictory to observations that we made with the UV macro photographs of the papers tested, the machine-made paper appears most susceptible to gel residue. And also, surprisingly, there's a greater amount of methylcellulose residue detected on the machine-made paper in the micrographs. And this kind of really had us puzzled, but we quadruple-checked our samples to make sure that we hadn't mixed them up during imaging, and we didn't, so we're confident that this is indeed the correct result. And again, the efficacy of the Japanese tissue barrier that we saw in macrophotography is reinforced by microphotography, with the exception of methylcellulose on machine-made paper. The next experiment, the clearance study, looked at another treatment variable aimed at reducing gel residues. This experiment compared gelling gum and methylcellulose, applied directly to all 3 papers at all 3 time intervals, with and without the additional clearance step of a damp swab. After gel removal, a swab was dampened with deionized water and lightly rolled over the paper samples 3 to 4 times. Here we have the UV macro photographs, and looking at the samples subjected to the additional clearance step with a damp swab, we observed subtle but perceptible reduction, or at least movement, of gel residues. And this seems to be true of both the gels. However, it may be somewhat more pronounced with the methylcellulose treated paper, the papers treated with methylcellulose. And again, we zoom in with the fluorescence photomicrographs. And in these images, reduction or movement of residue by damp swab is even more apparent, again with the exception of the methylcellulose on machine-made paper. And here, the machine-made paper sample raises a question. Where in the stratigraphy of the paper are these gel residues located? Especially when we compared UV macro photographs to fluorescence photomicrographs. If the residues are not readily detected with macrophotography, but are quite evident in microphotography, what's going on? Where's the gel? Have the residues migrated from the surface down deeper into the paper rather than being cleared? Without additional research and experiments, we can't really say, but it's clear that swabbing is having some effect. And our third and final experiment was the calcium acetate study. In this experiment, we only looked at gel and gum and the effects of varying calcium ion content in the gel as it relates to residue deposition. Our working hypothesis behind this experiment was that increasing the calcium ion content of the water used to prepare the gelin would increase cross-linking and result in a more rigid gel that would then deposit less residue. However, looking at our fluorescent photomicrographs, we observed that varying the amount of calcium acetate did not significantly alter residue deposition in this case. Fluorescence across the samples appears comparable whether we added 0 grams, 0.2 grams, or 1 gram of calcium acetate per liter of deionized water used to prepare the gels. In this study, the gel and gum, we prepared a concentration of 5% weight volume for consistency across our other experiments. However, we do feel it would be worthwhile to repeat this experiment using a lower concentration gelin, say 1 or 2%, where the presence of cross-linking cations is likely more critical to gelling. Higher concentration gels, like the 5% that we used, kind of presumably because there's more polymer present, may just have more physical entanglement. And now, briefly, I'm just going to give you a glimpse into some related ongoing research not described in the conference publication. So this work has been completed rather recently, is ongoing, and it's just a little bit of a teaser, I hope, of things that we'll continue to work on. With the presence of gel residue established, I conducted a preliminary accelerated aging study with instrumentation and assistance from the Getty Conservation Institute. This experiment used the same papers and polymers used throughout our residue studies that I just described. And a similar accelerated aging study, which included agarose and methylcellulose, was performed by Jeffrey Warda and others at Buffalo State College in the early 2000s. So the accelerated aging parameters that I selected, listed on this slide, are the same as those used in Warda's study, something I thought would be useful for comparing results. Here I'm showing you visible and UV macro photographs of the handmade rag paper samples treated with each gel before and after accelerated aging. One thing you'll notice looking at the control is that the paper itself has darkened slightly and become warmer in tone with aging. It's not terribly surprising. And under UV, fluorescence has diminished somewhat. As in Warda's study, agarose residue appears to age well, showing no perceptible discoloration under visible light. You do find some light tide lines under UV before aging, but to my eye they look much more like tide lines formed when applying a free water droplet, solubilizing and moving gelatin around to create a tide line. So I believe this has more to do with water diffusion than with the gel. The rag paper sample treated with gel and gum does exhibit increased discoloration in the shape of the gelin block applied. A very light brown discoloration observed under visible light, and I think it's just a little too subtle to see in projection. So if anyone's very curious, I brought the samples with me, and I'm happy to take a closer look. So curiously, we only observed light brown discoloration associated with gelin in the handmade rag paper sample and not in the filter paper or the machine-made papers. Started to wonder whether or not the presence of gelatin sizing had anything to do with this differential response. And with a cursory look in literature from the food industry, we do find discussion of gelin-gelatin mixtures. So this idea that the two materials may be interacting is not that far-fetched. Under UV, areas treated with gelin gum appear to exhibit increased fluorescence after aging. And this was observed across all 3 paper samples, not just the rag paper. And before moving on, I should quickly mention that I just learned of a very relevant dissertation just last week by a student from Bern, University of Bern in Switzerland, Corinne Huber. Corinne also investigated gelin residues on paper and conducted accelerated aging studies using elevated temperature RH. And she included ultraviolet and visible light aging as well, accelerated aging. She used a 2% gelin gum and observed noticeable color shifts following aging. This dissertation is in German, but I'm still hoping to get a hold of it, as it seems very relevant to our work. And recently, in an attempt to answer the question of where residues reside in gel-treated papers, we examined a few of our samples in cross-section using the fluorescence microscope. We looked at samples treated with gelin gum for 40 minutes without a Japanese tissue barrier. And what you see on the slide here is the Wattmann filter paper sample in both visible light and with the I3 filter cube engaged. Fluorescence throughout the sample does suggest that gelin residue has migrated through the entire thickness of the super absorbent filter paper. We don't necessarily expect this is the case with all of our samples, but admittedly cross-sectional imaging proved challenging, and so we haven't been able to look at our full set yet. We feel it's worthwhile to pursue this in the future, and I hope we do. So while quite a few new research questions were raised as we completed our experiments, we do feel that our study answered most of our initial questions, providing a few takeaways for conservators. Even though these are rigid gels, agarose and gelin gum do leave residue on paper. The properties of papers undergoing gel treatment definitely impact the degree of residue deposition. As with any conservation treatment, properties such as porosity, wettability, surface texture, and sizing and fillers should be taken into consideration. They may impact or modify the attraction of gel polymers to cellulosic paper fibers, and they can also be modified or removed during treatment. And finally, the Japanese tissue barrier layer was consistently effective in preventing or minimizing gel residue. And personally, I think I will continue to use it in my gelin treatments until we have a better understanding of how gelin residues age. I hope you've enjoyed this presentation. My co-authors and I have many people to thank for their support, especially staff in the Departments of Paper Conservation and Scientific Research at the National Gallery in Washington, Department of Paper Conservation at the J. Paul Getty Museum, and the Getty Conservation Institute. And I'd like to extend my personal thanks to Professor Richard Wolbers at the University of Delaware for sparking my initial interest in gel cleaning systems for works on paper. I'll start with you, Richard. So, thank you all for listening.